Hi there, let's look at the next couple topics, which deals with mass, weight, volume, and density. Uh, it's a huge misnomer the way the term weight has been used in society, because in physics, mass and weight are not the same. Mass of an object is the measure of the amount of matter that's in the object, and it's measured on the metric system in kilograms or grams, whereas weight is a measure of the pull of gravity, and we use a spring scale to do that, and it's always in newtons. And on Earth, because that's what determines the pull of gravity, the size of the Earth, mathematically, 1 kilogram is always equal to 10 newtons of weight. So if we had 2 kilograms of mass of a substance, that would be 20 newtons. So we can mathematically always find the weight if we know the mass. The other thing you need to know about mass and weight is mass never changes. If we have 1 kilogram of bananas, its weight is approximate, or it's 9.8 or approximately 10 newtons. If we move those bananas to now a smaller planet like Mars, what is the mass of the bananas? It's still the same number of bananas. 1, 2, 3 bananas, so it's 1 kilogram. But what about the weight on a spring scale? The weight would be less. So the weight here on Earth is about 10 newtons. The mass is 1 kilogram. The mass on Mars is still 1 kilogram. Haven't changed the amount of bananas, but the weight now is about 3.7 newtons because of smaller pull of gravity. Let's go to the moon. What about on the moon? What's the weight? It's even less, 1.7 newtons, because the moon is smaller. What's the mass? Still 1 kilogram. So mass and weight aren't the same. Let's talk about volume. By definition, volume is a measure of the amount of space occupied by the matter. And it depends on what kind of matter we have. Now, if it's a liquid, we would usually measure volume by pouring it into a device called a graduated cylinder. So this liquid would be about 7 milliliters. If it's a regular shaped solid, then we'd use the formula length times width times height. So in this case, if this was the three-dimensional rectangular box, it would be height of 2, length of 6, and width of 3. So 2 times 3 times 6, 36 centimeters cubed would be the volume. If it's a weird shaped solid, then we'd have to use the term displacement, which means the amount of water pushed away. So here is a graduated cylinder with some liquid in it, and we want to know how much this rock has for volume. Step 1, fill it up to 7 mils. Doesn't matter, it could be 10, but fill it up to a certain volume. Then dump the rock in and measure how much the volume went up now that the rock is in there. And so in this case, it's now at 9. So what would the volume be of the rock? 2 milliliters, or equivalent to 2 centimeters cubed. If it's a really big object, we'd use something like an overflow can first and then a graduated cylinder, because not everything fits into a graduated cylinder. So let's say we have a wood block. How would we measure the density? We'd go length times width times height with a ruler. A rock, we'd use displacement, so graduated cylinder. Oil, we'd pour it into a graduated cylinder. And a pen, we'd use displacement again. If we compare volume to mass of objects, let's do an experiment where we measure 10 mils into a graduated cylinder, take the mass of it, and then compare that to, say, something like salt water. Here's what we'd find out. 10 mils of pure water is 10 grams. 20 mils of pure water is 20 grams, and so on. And then salt water, 10 mils is approximately 12 grams, and 24, and so on. And we can chart this mass versus volume on a graph. And what do we notice about the slope of the three lines? Salt water had the steepest slope, and that's because its density is the highest. Vegetable oil, if we do that, had the lowest density and therefore not as steep a slope, and pure water, which always has a density of 1.0 grams, would be somewhere in between. Just a side note, we know vegetable oil has a fairly thick texture to it and it has a relatively high viscosity compared to pure water, but pure water is more dense. So viscosity isn't just about density or how tightly packed the particles, there's more to it than just that. So here we have vegetable oil, which proves that it is not as dense or it is lighter than water, so veggie oil. And here's pure water. And so veggie oil is less dense and sits on top at about a density of 0.92 depending on the oil, whereas pure water has a density of 1.0 grams per mil. So how do we find or calculate density? Well, there's a general formula we need to know. Density is equal to the mass divided by volume. So incidentally, let's say we looked at corn syrup with a microscope. Here's what the particles would look like if we had 1 cube of corn syrup compared to 1 cube of water. Then if this was the case about the particles, what would we say about the corn syrup? It was probably more dense. So density is a mass per unit of volume. There's an age-old question, almost a trick question. Which weighs more, a kilogram of feathers or a kilogram of gold? If you take the same volume of different substances, then they'll weigh different amounts. So there's 1 cube of wood, 1 cube of water, and 1 cube of iron. Which would weigh more when we put them on the scale? Which of these 3 substances? Well, the iron, probably. Iron is, if they're all the same volume, then would they all have the same mass? No. In fact, we know what this would weigh. 1 cube of water would weigh what? 1 gram. How about wood? Would it be more than 1 gram or less? Well, wood floats on water, so it's going to be less than 1 gram, given that we know floating and density are related. Less than 1 gram. In fact, 0.5, 1 gram, and of course, this is the highest, 8 grams. So, which has the greatest mass and therefore the most dense? Da-da-da, iron. So here's our equation, mass in grams divided by volume in centimeters cubed. If we use kilograms, then we have to use kilograms cubed to keep it equivalent. So liquid water has a density of 1,000 kilograms per cubed, while ice has a density of 920. Calculate the volume of each. We'll do that later. So the density of a regular shaped solid, we'd go length times height times width. And if its mass was 240, what would the density be? So mass is 240. We don't know the volume, but we can find the volume. The volume is 2 times 3 times 4, so 2 times 3 times 4. So that's 6 times 4, that's 24. So 240 grams divided by 24 centimeters cubed is 10 would be the density of this block. 10 grams per centimeter cubed. We need correct units. So here's a comparison of the densities of various substances. Now, floating and sinking are a good way to double check how density works. Oops, gone a little far. Let's go back up. And scroll down to this screen. Here's a device that we often will use to measure the density of substances, and it's called a hydrometer. So hydrometers will float higher up in fluids, liquids that are more dense. So the higher up it goes, so let's say it floats a little higher, that would give an even higher density. So density is the measure of the compactness, the proximity of the atoms. So there's the compactness. Pretty amazing, eh? Lead floats on liquid mercury. So this cue ball is floating inside this cup of liquid mercury because of mercury so dense. Ice floats on liquid water. Ice is less dense than liquid water. That's why lakes and ponds have thin layers of ice covered in the winter. So there are several factors that would allow us to change the density of a substance. One is temperature. So the higher the temperature, the lower the density because the particles are farther apart, less compact, with the exception of ice, of course. And pressure. The higher the pressure, the higher the density because they're forced to be in a tighter, compact situation. And also the amount of dissolved solids in the liquid, so how concentrated it is. Salt water has lots of dissolved substances, whereas pure water doesn't. Let's finish with a video clip about volume and density. And it's located, there it is.
Eureka! This unit is divided into 3 programs. The program you're about to see is on volume and density. This will be followed by buoyancy. And the third and last program in the unit will be on convection itself. But our story begins with volume and density. What does the word volume mean? What does the word density mean? Well, imagine that you're a junk car dealer and you want to send these 8 old wrecks to the steel yard for recycling in this container. The only trouble is they're full-size cars and they won't all fit in. If only they were tiny little compacts, there'd be no problem. But they're not. That's only a dream, so it's time for the car crusher. But wait, how small should you crush them so that they'll fit exactly into the container? Well, how big is the container? 4 meters? No, that's only its height. What you need to know is how much space there is inside it. Look at it this way. The outsides of the container make up a sort of envelope. What you need to know is how big the space inside this envelope is. Or rather, if we use the Greek word for envelope, how big the volume is. Because that's all the word volume means. How much space a thing envelops. The easiest way to work out the volume of something like a box is to measure not only its height, but also its length and its width. And then multiply all these together. 4 times 4 times 4 equals 64. The container has a volume of 64 cubic meters. And since you have 8 cars that you want to fit into it, you'll have to reduce the volume of each car to exactly 1/8 of 64 cubic meters.